So, welcome everybody. Today we continue our discussion of topological spaces, and we continue with the basic definitions. So it was remark 1.9. So I have written that we consider a Hausdorff space, but of course all the definitions are okay also just in a general setting. I just didn't want to go very deep into small fine things which may appear in the general setting. So let us restrict ourselves for a moment to a Hausdorff space. So last time we have discussed limit points and adherent points of a set in a topological space. Now a new definition that a set in a topological space is closed if its complement is open, that is belongs to the topology. Okay. Exercise, closed sets have the following properties. A union of finitely many closed sets is closed, and intersection of arbitrarily many closed sets is closed. So this is a kind of dual properties to the properties of open sets, and everything can be obtained from the properties of open sets and De Morgan laws about the interrelation between operations of union, intersection, and taking the complement. Okay, so everything should be more or less clear here, and we go further. The next notion is the closure also should be known, but nevertheless we repeat. So the closure of a set is the smallest closed set containing A, and we use this notation for the closure. And the exercise is that the closure is the same as the intersection of all closed sets containing A. And it is, I hope that this identity is more or less clear, because we have just mentioned that the intersection of any amount of closed sets is again a closed set. And of course, this is the smallest closed set containing A, because all sets containing A are considered in this intersection. So this should be clear. And this is what the exercise is to show this, that the closure of A, it is unified with all its limit points. Or this is the same via the definition of adherent points and limit points. So this union is nothing else but all adherent points of A. So this is also a kind of known things, hopefully. Yes?
Yes, I think we are familiar with this.
Yes, perfect. We go further. One more definition. So if the closure of a set is the whole space X, then A is called dense in X. This also should be known. Okay, and one more definition. X is separable topological space if there exists a countable dense set in this space. Also, natural generalizations from the setting of metric spaces. Okay. Now recall the notion of continuity in the setting of metric spaces. So we have two metric spaces, X with the metric dx and Y with the metric dy. And we have a mapping from X to Y. I recall that a mapping F is called continuous at some fixed point X in the first space X. If for any epsilon there exists delta, if for any positive epsilon there exists delta positive, such that for all X prime in X, such that this distance between X and X prime is smaller than delta, we have that the distance between f of x and f of x prime is smaller than epsilon. What is written here? Here it is written that x prime belongs to the delta neighborhood, open delta neighborhood of x. And what is written here? Here it is written that f of x prime belongs to the epsilon neighborhood of the point f of x in the space Y. So what is the statement? That for all elements of this delta neighborhood of X, their images belong to the epsilon neighborhood of this guy. That is, we see that the mapping F maps this delta neighborhood of X totally inside epsilon neighborhood of f of X. Okay, so this motivates the definition of continuity. And this will be our definition 110. So let X tau X y tau y be two topological spaces. And let f from X to y be a mapping. Be a mapping. F is called continuous. At a point small x in the big X. If for each, we consider only open, but I keep on writing it open, for each open neighborhood U of the point f of X, this is a neighborhood, is a subset of the space Y. Or I can even write down like this, tau Y. Open neighborhood of the point f of X. There exists and again open neighborhood Ux. This is an element of tau X, the neighborhood of the point X, such that the mapping F maps the whole neighborhood Ux inside the neighborhood UF of X. So this is a kind of continuous at a point. And now we can say that a mapping is a continuous. The mapping F is continuous if it is continuous at each point. So what we have done, we have just replaced open balls by just open neighborhoods. And we also can consider notation. So the space of continuous mappings from X to Y. The space of continuous mappings from X to Y. Okay, so I hope the definition is totally obvious. And then a small remark concerning it. So may I turn the page?
Okay, I already read down all the things.
Yes, yes. It's
Okay.
fine.
Okay. So remark. So a mapping F is continuous, so in all points, if and only if the following holds, that is pre-image of any open set here in this topology, so in this space. So for any open set here, its pre-image is open here. This is the first statement, and then the second statement is that the same holds also for closed sets. So pre-image of any closed set in Y is closed in X. So let us try to argue this. So let us show this and how to do it. So in one hand, so this is one direction, and I hope that this direction is rather obvious. Namely, we take any point x, we take any point x and any point and then corresponding f of x. We take any v which contains f of x and open, so v from tau y. Then if we consider its pre-image, it is open by our assumptions, and we know that it contains x by the properties of pre-images. And obviously we have also that f of this pre-image is just v. So it is included in v. So everything is fulfilled in the sense of definition. That is, the definition of continuity in the point x is satisfied, and this can be done for any point. So you are agreeing that everything is clear, and I don't need to write down the text.
Yes.
Yes.
Okay, then the opposite direction. So we assume that the function, so the mapping f is open by this definition. Okay, and what we need to show that the pre-image of any open set is open. So let's, let V be an open set in Y, that is, it belongs to the tau topology. So let me make it like this. Okay, so let V belong to tau Y. Consider its pre-image. We want to show that this is an open set. Yeah, but now it's just a set in X. Consider any X, any element X belonging to this pre-image. That is, we can consider this pre-image as there is a neighborhood of X. Then, by the definition of continuous mapping, then by the definition of pre-image and image, we know that, that f of x belongs to V. That is, V is a neighborhood of f of x. Okay. So since V is a neighborhood of f of x, then by definition of continuous mapping, there exists a neighborhood ux, it's a neighborhood of x, such that the whole ux under f appears inside V. Yeah, so this is the definition of continuous mapping. So F is a continuous mapping. So if we have a point f of x and some open set containing it, then there is a neighborhood of x such that f of the whole neighborhood belongs to V. Okay, but what does it mean? Using the properties of prime images, this means that this ux, the whole ux belongs to the preimage of V. Yeah? Is it clear?
Yes, yes, pretty
Yes.
clear.
Yes, but what we have shown, we have taken just an arbitrary point in this set, and we have shown that this point is included with some neighborhood, open neighborhood. That is, this set contains all its points together with their open neighborhoods. This means that this set is open. Okay, is everything clear or some comments are needed?
I think it's clear.
Yes, it's clear. Okay.
Okay, now a few words about this this step. So this step is obvious because we just use again the properties of pre-images, that pre-image of a complement. So if V is open, then its complement Y minus V is closed, and this is just the complement of the pre-image of V. So that's why these two statements are equivalent. Okay. So let us go further. Remark. So continuity, as it was defined in definition 110, is in a sense continuity in the sense of Cauchy. So usually at the first semester there is mathematical analysis, and people discuss continuity with in the sense of Cauchy and also in the sense of Heine. So recall what does mean continuity in the sense of Heine. So a mapping F is called sequentially continuous or continuous in the sense of Heine at a fixed point x if for any sequence in the space x which converges to this point, fixed point x, we have that the images of this sequence under the image of the sequence under F is a sequence which converges to f of x, and then the convergence is in this space. So convergence of all sequences. So in the course of analysis 1, mathematical analysis, when everything is considered for the case when we have R here and here, and with standard topology generated by the standard metric, then we know that these two notions coincide, continuity in the sense of Cauchy and continuity in the sense of Heine. Of course, it does not need to be so in the general setting of topological spaces, namely, if f is continuous, so continuous in the sense of Cauchy, in the sense of this definition, if f is continuous, then f is sequentially continuous. The opposite is not true in general. So the topological spaces should be not too large, not too fat to have the equivalence. In particular, in metric spaces, these two notions are equivalent. And yes, so last time one of listeners has mentioned that we can use nets instead of sequences. Yes, so net is a generalization of a sequence where instead of the set of indices instead of natural numbers as indexes, we can use any directed set, like we consider a kind of x lambda, where lambda belongs to some index set, and if this set is directed, so we can understand, we have make a meaning to this notion, to something, when lambda tends to some lambda 0, and all these guys belong to this directed set. So in this setting, the set of indices does not need to be countable. It can be uncountable and very, very fat. And then when we use, so to say, continuity using such objects instead of sequences, we obtain the notion which is equivalent to the notion of continuity in the sense of Cauchy, that is in the sense of using neighborhoods. Okay, but in the sequel, we don't need nets. We will consider only what we really need. So be careful. Sequential continuity is something different and a weaker notion. Okay, so next exercise, we will not discuss it. It's really a home task. So if X is a space of continuous functions defined on the interval from 0 to 1 with a standard supremum norm or supremum metric, and we consider real valued mappings from this space. Real valued, again, real numbers with standard topology, standard metric. Then one can practice himself or herself by showing that, for example, such mappings are continuous in the sense of this definition. Okay, we go further. And next notion, which again, a generalization from the setting of metric spaces. So first, let us recall what happens in metric spaces. So if we have a metric space and a set in this space, we say that this set is bounded if there is a number R, strictly positive, a real number that is finite number, not infinity, such that A is is inside this ball with centrum at 0. So we can cover this set by this ball with finite radius and centrum at 0. Of course, there is a generalization of the notion boundness for topological spaces. This is the so-called von Neumann boundness, but we don't need it so far in the frame of this course. That's why this is just a keyword. You can find it if you wish. But what is interesting for us is bounded mappings. So this is the definition. And we are interested in mappings from X to Y, where X is a topological space and Y is a metric space. So typically just R with standard metric or Rn with standard metric. So something nice. Okay, so we consider such a mapping, and this mapping is called bounded if f of X, it is now a set, the image of the whole space under F. This is the set in Y, and Y is a metric space. So in the metric space, we know what does mean a bounded set. So the mapping F is called bounded if the image of the whole space under this mapping is a bounded set in this metric space Y. One can also formulate this boundness not in terms of a ball with some fixed radius and centrum in 0, but one can also say that a set is bounded if its diameter is bounded. And diameter of a set, it is just supremum of distances between 2 points of this set, and supremum is taken over all couples of points in this set. So if this diameter is finite, the set is bounded, and of course you can just if you can calculate the diameter of a set and you see that it is bounded, then you can create the corresponding radius such that the whole set is covered by such a ball. But by adding this diameter to a distance from 0 to any point of the set. And again, a standard notation that CB of X, it is the space of all bounded and continuous mappings from a topological space to a typical real numbers with standard metric. Standard metric is like this. Okay. So now the definition which we are going to write down, definition 114. Let me find this in my notes. Okay. So let X be a non-empty set. Let tau1 and tau2 be two topologies. Be topologies on X. So we have two topologies on X. If tau1 is a subset of tau2, yeah, so tau1 is so each topology is just a system of sets, which are subsets of X. A system, of course, satisfying some assumptions, but still a system of subsets of X. So sometimes we can compare two systems of subsets of X. So if we have this inclusion, in this case, then we say that tau2 is stronger. There are also some other notions, so also finer or larger. All notions can be found in the literature. Then so tau2 is stronger than tau1, and tau1 is weaker. And again, there are some synonyms: coarser or smaller. These things are synonyms, they mean the same. Then tau2. Of course, it is not always possible to compare two topologies, but if this happens, if they are comparable, then one is stronger, one is weaker. Okay. What else should I say? Okay. So probably can you imagine the strongest topology?
Discrete topology.
Yes. So let us write it down. So tau, which is equal to all the space, the set of all subsets of X is the strongest. It is the discrete topology, and the weakest is what is the weakest?
Empty set and the whole set.
Yes, and this is what was the trivial one. The trivial topology is the weakest. Okay, so small exercise. Of course, at home, consider X which consists of 3 points X, Y, and Z, and find all topologies. Of course, you don't need to distinguish the topologies where you change the roles of X and Y and Z. So substantial, find all substantially different topologies which are comparable. Comparable means that there is something like this, which are Hausdorff, So this is just a playing. So a good exercise. Okay. So let us go further and let us play with some topologies. So may I go further? Next page.
Yes.
Yes.
Okay, so first a remark. So one can compare topologies using, so not all the sets. So sometimes it's probably hard to check this, but sometimes one can compare topologies using neighborhood bases. So we have already discussed what does mean a base of topology. I'm not sure if I can find it. Sorry. Probably I should not try to find it, but last time we have discussed, I remember, the notion of a base or basis of topologies. So let tau 1 and tau 2 be two topologies on a set. We can consider also local bases of each of the topology at each point. What does mean local base? So a system of sets is called a local base of the corresponding topology at a fixed point if it is a base for the set of all neighborhoods of this point X in the sense of the corresponding topology. This means that for any neighborhood of this fixed point, there is a set from this system which is contained in this neighborhood. So like in the metric space, if we have metric space, wait, it is not so nice. If we have a metric space and we take a point X, and then we can consider, for example, such balls for radius 1 with radius 1 over n for all natural numbers n, and this is a nice base of neighborhoods of the point X in the standard topology of a metric space. Okay, so now if we have two topologies, we can compare their local base. So this thing, so the topology tau 1 is not stronger than topology tau 2. So because here I have also this. If and only if for all points of the set X, each open set U1 in this local base in the topology beta 1 contains some open set U2 from the base which corresponds to the topology tau 2. So if tau 2 is stronger, it has more open sets. Hence, it is natural to assume that a stronger topology should have more neighborhoods, but this means that it should have also more nicer neighborhoods, that is smaller neighborhoods. Okay, because when we are interested in limits, so if a point X is a kind of a candidate for a limit, we should approach it very well by using the neighborhoods. Yes, so the more neighborhoods we have, the more effective we should be able to approach each point X. This means that a stronger topology, a better topology, should provide more neighborhoods to reach X, to approximate. No, not approximate, to... Yes, but hopefully you have understood what I mean. So it is written here in a careful way. And let us consider an example. So as a space X, we consider R2. As tau 1, we consider standard topology, which is generated by the Euclidean metric on R2. So this is the Euclidean metric. This is the norm in L2 in the space R2. So X and Y are vectors with coordinates x1, x2, and y1, y2. This is the Euclidean metric. And consider another topology, tau 2, which looks as follows. So let me probably draw. So we have our R2. So this is R, this is also R, and the whole picture is R2. So what do we have? We take any open set U in R, so with respect to the first coordinate, and we consider a cylinder this is the set U times R, so cylinder. So this is a set of this type. So we consider this system, which consists of empty set and all cylinders of this type. And so the first statement that tau 2 is a topology. So is it obvious? Is it clear that it is so?
Yes, it's pretty clear.
Perfect. Then you see that all open sets, which are not non-empty, yeah? Non-empty open sets are cylinders. And in particular, they are unbounded. So next question. So is this topology Hausdorff or not Hausdorff? This is my question to you. You are welcome to answer.
Not Hausdorff.
Yes, that's right. It is not Hausdorff. Is not Hausdorff because, for example, if we take 2 points with the same first coordinate, we are not able to separate them by using only cylinders of this type. We cannot separate, for example, x1, x2, and x1, x3, where x2 is not equal to x3. Okay, so now let us try to compare this tau 2 with tau 1, the standard topology in R2. So what would you say? Are they comparable? Which topology is weaker, which is stronger, if they are comparable?
I think tau 1 is stronger.
Yes, so they are comparable and tau 1 is stronger. So tau 1 is stronger than tau 2. How to show it? Well, first of all, I hope it should be obvious that these sets, they are open in tau 1. So if U is open in R1, then this set is an open set in the standard topology in R2. That is, we have that tau 1 is a subset of tau 2 is a subset of tau 1. But they are not equal because, as I said, all open sets in tau 2, they are unbounded. And we can use this remark. So we compare two bases. So for the standard topology, base look like this. One of possible bases. So if we have a cylinder in any cylinder and the fixed point x, so let me I don't know, let me take a point x and fix it. So for any cylinder open set containing, for any open neighborhood of x in the sense of topology tau 2, we are able to find an open wall with sufficiently small radius around x. So any open set, any open neighborhood of x in the sense of tau 2 contains, includes an open set or open neighborhood of X in the sense of this topology, tau 1. But the opposite is not true, because if we take any X, okay, let me draw it separately. So we take X, we take open ball, so this is Ux in the topology tau 1. We cannot create any unbounded cylinder which could be inside this open ball, because cylinder is unbounded. So just using this comparison, we also see that there are not enough open sets in the topology of tau 2 to be equivalent to the topology tau 1. Okay, let me kill this dummy picture. But now let us consider topology tau 3. So if we consider tau 3, which is the smallest topology containing the sets, so U times R, but also R times U. U is open in R. Then tau 3 is the same as tau 1. That is, if we allow not only cylinders which are, so to say, vertical, but if we allow also cylinders which are, which color should I take? I don't know, which are horizontal. This means that the intersection of such two cylinders is a nice, I don't know, bounded set. And having both types of cylinders, we can control both coordinates of points. So these cylinders allow to separate second coordinates of points, and this type of cylinders allow to separate first coordinate of the points, and we are able to create bounded sets. And then again, compare using this comparison, we see that, roughly speaking, in all such set, we can find a circle, which is a ball open set in the base of tau 1. For any open ball, we can find this rectangular, which is a object of tau 3. So hence, these two topologies are comparable and they are actually equal. Okay. So is everything clear here?
Yes, yes.
Perfect.
Yes.
So may I go to the next slide?
Yes.
Yes, yes.
Okay, so let us go. So consider, so we are still working with the same example, and the next step, so consider the mapping P1. This is the mapping from R2 to R1, which maps the whole vector with coordinates x1, x2, maps onto the first coordinate. So this is the canonical projection. P1 is the canonical projection on the first coordinate. Then this mapping P1 is continuous with respect to which topologies? We have now tau 1 and tau 2. With respect to which topologies this mapping is continuous? So it is my question to you. of course, here we consider the standard metric. So we consider, probably I should write down so we have R2 with topology tau I, and the mapping is to R1 with the standard metric. So what about the continuity? So is P1 continuous with respect to standard topology?
At least when we choose tau1, it is continuous.
Yes. Yes. But actually also tau2, since for any open set U, for any U open in this space R1 with standard topology with isometric space, for any such open U we have, what is the pre-image of this open set U? This is exactly the U times R, and this is the element of tau2 and also tau1. Yeah, so these cylinders, as on the picture, it is exactly the pre-image of the set U with respect to this canonical projection P1. And hence the pre-image of any open set, the pre-image is open. Yeah, so by definition, not by definition, by our remark, which we have proved just a few minutes ago. So we have proved this, yes? Remark 111. So the mapping is continuous if the pre-image of all open sets are open. So this is exactly what we are doing here. So pre-image of any open set in R is the cylinder. Pre-image with respect to this canonical projection. This cylinder, it belongs to tau2 and also to tau1. So this projection is continuous with respect to both topologies. Now consider P2. This is again a canonical projection, but on the second coordinate. So again, write that it's the mapping from R2 with sum of topology, which we are looking for, which we are interested in, into R1 as a metric space. So a vector with coordinates x1, x2 is mapped to its second coordinate. Then, what about this mapping? It is continuous when? In which topology? Topologies? So we compare tau1 and tau2 again.
I think it's continuous in tau1.
Yes. What about tau2? Is it continuous in tau2?
No, I don't think it's continuous in tau2.
Yes, that's right, but not in tau2 since for any open set U in R1D, we have that the pre-image of this open set with respect to the projection P2, this is a cylinder of the type R times U, and this guy belongs to tau 1. It's an open set in the standard topology generated by Euclidean metric in R2, but this set does not belong to tau 2 if U is not equal to R itself. Okay, so you see that when we consider different topologies, the amount of continuous mappings also differs. And let me mention that, so let me mention it here. That tau 2 is the weakest topology such that P1 is continuous. So P1 is continuous in both topologies, tau 1 and tau 2. Tau 1 is smaller, tau 2 is smaller than tau 1. And actually it is the weakest. Why? Because in order for this mapping to be continuous, we need that all pre-images of open sets should be open in the topology in X. But yeah, so tau 2 is the weakest topology which contains all such sets. Yeah, looking at the definition. Okay. Of course, if we consider tau 3 as before, then again both projections are continuous with respect to tau 3. Good. So is there any questions concerning this example?
So the weakest topology to make a function continuous is a topology generated by the preimage of this function.
Yes, preimage of open sets with respect to this function. But you have used the proper word, generated. So it is not always such simple as here. But the smallest topology which contains all pre-images of open sets, yes, is the weakest topology such that this mapping is continuous with respect to this topology.
Okay, thank you.
Okay, so let us make a kind of a summary. So if we have two topologies on a set X, and if one topology is strongly weaker than another one, so tau 1 is strongly weaker than tau 2, then, so some conclusions. So first of all, there are more tau 2 open sets than tau 1 open sets. It's obvious because here we have this. So here in this system, there are more sets than in this system. That is, there are more open sets. Since in tau 2 there are more open sets, this means that there are more complements. And hence there are more tau 2 closed sets than tau 1 closed sets. So is it clear with these statements?
Yes.
Yes.
Okay, now the next statement. We consider mappings from X to Y. Y is just some extra topological space, it is fixed, and we play with topologies in X. So we consider either tau 1 or tau 2 in X. So the statement is that if we consider tau 2 as of the stronger topology, then there are more continuous mappings than if we would consider the weaker topology. Why it is so? Because once again, for the mapping F to be continuous, this means that all pre-images of the sets from this topology, so V belongs to this topology, tau Y. So if F is open, all such pre-images should be open sets. But the more open sets we have in X, the more chances we have for such sets to be open. Yeah, so the bigger topology is here in X, the easier it is for the mapping F to satisfy the condition that the preimage of open sets tau y is fixed. Yeah, so the more open sets are here, the more chances have this set to be open. So is it clear?
It's clear. Yes.
Yes, it's clear.
Yes, but on the opposite direction, so if we consider mappings from a fixed topological space to our space X, and we play with topologies here, tau 1 or tau 2, then the bigger topology is here, the fewer continuous mappings we have. Again, why? Because the more open sets we have here, the more preimages we should consider and require that these preimages are open here. So it's more and more difficult. It becomes more and more difficult if this system of sets becomes larger and larger. So you see, playing with topologies, we can also, in a sense, control how many continuous mappings we have and continuous in which sense. Okay, are there any questions so far? Is everything clear?
Yeah, it's clear.
Clear.
Okay, good.
Yes.
Then we go further and we consider example. Oh no, one more remark. Remark 118. So let tau 1 and tau 2 be two topologies. So topology tau 1 is not stronger than topology tau 2 if and only if the following holds. Namely, we consider the identity mapping between X with tau 2 and X with tau 1. So the identity maps each point X onto itself. So the statement is that if tau 1 is not stronger than tau 2, then such mapping is continuous. So you see so hopefully it is obvious, but I will try to understand, to clarify what does mean that this mapping is continuous. This means that any open set which belongs to tau 1, that is here, its preimage, but its preimage is just, so identity X preimage of U, this is just U, because we use identity map. So we require that, so since this mapping is continuous, we require that for any open set here, its preimage is open here. But this is exactly the case when we have this inclusion. Okay, is it clear with this statement?
Yes, yes.
Yes.
Okay. Then the next example should be example 119, but we will survive. So product space and product Tikhonov topology. So let T be an index set, arbitrary large. For each T in this index set big T, let us assume that for each such T, there is a topological space, which is non-empty. Topological space, that is, we have a set and a topology on this set. And this is given for each parameter T from our index set T. Then we consider Cartesian product of such sets. And what does it mean? So this object, the Cartesian product of such all these sets, is the set of elements or collections of the following form. So one may say that this is a kind of vector with so many coordinates. So each coordinate live in its own space, its own set. So xt belongs to big xt, And this is true for all indexes. So it's a kind of vectors with probably uncountably many coordinates. But since we don't speak about linear spaces or vector spaces, we don't call it vector, but we call it element or collection. Okay, so we consider this Cartesian product and we define the product topology. So as open sets on this set, we consider empty set and all arbitrary unions of sets of this form. Where, so how looks this set? It's a product of UT for T in some selected subset T0 times the product of xt for all indexes which are not in this T0. The requirement is that T0 is finite. All UT are open sets in the corresponding spaces. That is, roughly speaking, these sets are, again, a kind of cylinders. Sorry for my not nice drawings, but probably we can draw it like this. So here we have a kind of this is U1, this is U2, so this is their product. And then we have a kind of cylinder with respect to the other coordinate. So you may guess what happens further. So it's a kind of cylinder, so the base is finite, so finite dimensional. That is, we have only finitely many coordinates, which are restricted by some fixed open sets. But with respect to all other coordinates, we have the whole range. That is, the whole space is taken. Well, I don't like my drawing, so let it be like this. Okay, so these guys are cylinders. And so we consider arbitrary unions of set, and this is the exercise that these empty set and arbitrary unions of sets of this form, these are really a topology. And this topology is called product topology, and I will denote it by tau. So the product space is this Cartesian product with this product topology. So exercise that tau is really defined in this way, that open sets are of the form with these requirements, then tau is really a topology. Okay, but actually one has to show that the intersection of two of these sets, of two of these cylinders, can be represented as an arbitrary union of such cylinders. Okay, so caution, if T is not a finite set, then the sets of the form, just a product of open sets for each coordinate T, we take any open set in the corresponding topological space and consider their Cartesian product. So if this index set is not finite itself, such set that does not belong to product topology. That is, this set is not open in the product topology, except, of course, the case when all except finitely many UTs coincide with XTs. So the topology which is generated by these sets of this type is called box topology, and you can learn about it more if you wish, but so to say, the canonical topology and the right one and the proper one is the product topology, which is generated by cylinders with finite dimensional bases like this. Okay, next, so if all topological spaces which we take into the Cartesian product, if all of them are Hausdorff, then the product space is Hausdorff as well. So let us prove it. Proof. So let us what happens today? So consider, so this symbol means consider. This is like an I from the side. So consider X and Y 2 points in our space, this product space, and these 2 points are not the same. What does it mean? This means that they differ at least at one coordinate. That is, there exists at least one index T0 in our index set, such that the coordinates x T0 is not the same as the coordinate y T0. Okay, but we know that each topological space is Hausdorff. So inside x T0, we can separate these 2 coordinates. So what happens further? There exists ux T0 and uy T0. There are 2 open sets in the topology tau T0, such that x belongs to ux T0, y belongs to uy T0, and these 2 guys, these 2 neighborhoods, do not intersect with each other. Since x T0 tau T0 is Hausdorff. Okay, now we can consider the following cylinders in the product space. U T0x times products of txt over all t. Let me write it in the red color. Over all t which are not equal to T0. In the same way, we consider uy T0 times product of xt over all t which are not equal to T0. And these 2 sets, they belong to the tau, so to the product topology. Yeah, and they separate points x and y. So roughly speaking, to understand what's happening, it's like this is my T0 coordinate, and we have 2 points, x T0 and y T0, and then we have several cylinders. One cylinder which is around this point, and another cylinder which is around this point. And they do not intersect, and they separate these 2 points. But cylinder yeah, you see in so many, probably uncountably many dimensions. Okay, so that's it with Hausdorff, with the property of Hausdorff. Is everything clear?
Yeah, it's clear.
Yes.
Okay, let us go further. Yes, so if our index set is countable, that is, we can enumerate it like a sequence of points, Tn. So this is the first if T is countable, and if all topological spaces are metrizable, that is, the topologies are generated by some metrics, so we have a sequence of metrics. Then the product space is metrizable as well. So we can offer some candidates for such a metric. For example, this one, so dxy is just a sum of n from 1 to infinity to 2 to the power minus n times minimum between 1 and distance dn, and we use tn coordinates of x and y. X and y are vectors in x. Or we can take another metric like this. Again, t to the power minus n times, and here dn, so distance between the tn's coordinates. But we should make this expression bounded, so we divide it with like this. So this is a kind of, what do we see here? So we have countably many coordinates. So at least, I can say at least countable. Also in the finite case, it's also okay, no problem. So we have countably many coordinates in our vectors of this form. And then if each coordinate, so to say, belongs to a metric space with a metric dn, then we can create a metric on the product space like this. So we take into account each coordinate. So the sequence of vectors converges in the sense of this metric, vectors in this product space, if it is converges coordinate-wise. So we so to say control each coordinate, take into account the distance between two coordinates of two vectors, make this expression bounded like this or like this, and then we take into account all of them, how to make all of them. So we sum them up with some weights which allow this sequence, this series to converge. So this is one. So these are the standard choices. And you see, once again, I stress it, that the convergence in this case, in this space, is the same as coordinate-wise convergence in each of the space of the product. So exercise for you to show that this is the proper metric in the sense that the product topology is exactly the topology generated by any of these metrics. Of course, you can invent some other versions of these metrics. Okay, let us go further. Everything is clear here?
Yes, yes.
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 So, once again, under two conditions, we have that this guy is metrizable, but if T is uncountable, then this product space is non-metrizable. And so this is a kind of one of canonical examples of topological spaces which are not metrizable. Yeah, so we are really beyond the setting of metric spaces. So how to prove this statement? So proof looks as follows. So if a topological space is metrizable, then it is first countable. I recall that first countable means that each point has a countable neighborhood basis. That is, if we have a, I don't know, topological space, which is a metric space with a metric D, then we take any point y in this space, and then this is a nice base of open neighborhoods around this point. Yeah, so if a topological space is metrizable, then there is a metric, then we can construct such balls for each point, and then we have a countable neighborhood basis. So everything is fine. But what happens in our case if our T is uncountable? In this case, we cannot have, so let me write down. If T is uncountable, then, for example, the point 0, no, 0 is a bad point because we are not in the linear space. Then, any point x in this x cannot have a countable. So neighborhood basis, it's a local base. Local base cannot have a countable local base since what is x? So once again, ix is the element of this form. So this guy has uncountably many coordinates. But our open sets, they have this form. So these are the basic open sets, yes? And so you see from this form, they are cylinders. That is, they control only finitely many coordinates. So it is not possible having only countably many cylinders with finite bases, that is, which control only finitely many coordinates. It is not possible to control all uncountably many coordinates. So I'm not sure if everything is clear what I have said.
Yes, yes.
So let us write down since basic open sets control only finitely many coordinates. So really, in order to, so to say, to reach the point x, you have to run uncountably many neighborhoods, basic neighborhoods. So this is the crucial thing. And this is the way where this sequential continuity and continuity are not the same notion, exactly because of this story. That to reach the point, you have to visit, so to say, or you have to use uncountably many neighborhoods. Okay. What I wanted to say further. Yes. So again, consider canonical projections. For each coordinate t0, let us consider the canonical projection from the product space to its t0's coordinate space. That is, the element with all vectors with all coordinates is mapped to its t0's coordinate. This is the canonical projection, and now we may consider so many of them. So for each t0 in T. So the statement is that the product topology tau is the weakest topology such that all such canonical projections are continuous. So coming back to our example 116. Where it was? Yes, so we have tau 1, tau 2, and tau 3. So tau 2 was the smallest, the weakest topology, such that the projection P2 is continuous. Actually, tau 3 is the smallest topology, such that both projections P1 and P2 are continuous. And we have this. That is, the standard topology is the weakest topology where all projections are continuous. But this was the case where we have only product of two spaces, yeah, R times R. So we have a Cartesian product of only two spaces. It's fine, but if we consider a product of infinitely many spaces, then exactly the product topology is the right topology in the sense that this is the weakest topology such that all canonical projections are continuous. Okay. And once again, why? Because again, we take any open set in tau t0, then the pre-image of this open set with respect to the corresponding canonical projection is just u times product of all xt over t is not equal to t0. And this is a nice element, basic element in this product topology tau. Okay, everything clear?
Yes, yes.
Yes.
Okay. If all topological spaces xt tau t are the copies of the same topological space x with some topology t on x, then this Cartesian product is just this power of the same space x. So we have so many copies of this x, it's like tth power of x. But this is nothing else. So once again, this is the object. This is the set of elements of this type where each coordinate xt belongs to the space x. So this is nothing else but the set of all mappings or functions from t to x. Yes? So this is just like x of t for all t. So this is an important space also for stochastics. For one can consider it as a space of all paths of stochastic processes. So this is our time, and this is where our random variables take value. So state space of random variables. And then this space with this Cartesian product is the space of all paths of stochastic processes, or the set of all functions from t to x. In this case, moreover, a special case of this setting. So all topological spaces are the same. And actually, this x is nothing else but real numbers with standard metric. So in this special case, the basic open sets, so the cylinders, so these open sets, they look as follows. So I have just rewritten these objects in a more natural way for functions. So basic open sets for this product topology looks as follows. So open set, it's a neighborhood of the point x. This is a kind of radius of our, it's not a ball, it's again a kind of cylinder, yeah? So it's a radius of cylinder. And these are finitely many coordinates which we control. So these are all functions defined on T such that their is coordinates, so they are fixed, these n coordinates are fixed. So these corresponding coordinates are not, so they belong to the, what does it mean? This means that y ti belongs to the epsilon neighborhood of x ty. Okay. So this is the standard cylinders in this special case. And of course, we vary the number of points, but they are always finite number. So we, for all natural numbers, but fixed, we vary different points of our index set. And of course, we'll consider all possible epsilons to have this epsilon neighborhood. For example, what would it be in the case if we have x equal to 0, just identically 0 mapping? Let us assume that we have, I don't know where to draw. I don't know why I like to draw, but nevertheless. So let it be my t. So my zero function is just zero function, it is here. So then we fix some coordinates, so t1 Okay, T2, Tn, and we fix this epsilon. So we make these like barriers of size epsilon at these coordinates. And so to this neighborhood of the function which is identical to 0 belong all functions which go to these barriers. So they can be very big between the points, but they should cross these barriers. Okay, I don't know if you see anything on my picture, but I hope that you understand the idea. Well, so these are how these cylinders look in this particular case. And on the base of this basic open sets, you can easily, or not easily, but sufficiently easily solve the following exercise. So you should show that the product topology, in this case, in this particular case, corresponds to the pointwise convergence. That is, a sequence of functions converges to a function x in this product space, which is like this, if and only if these functions converge coordinate-wise, that is, at each point, at each time point. Okay, is there any question concerning this?
No.
No. Then exercise that if we consider the space of all continuous functions defined on the interval from 0 to 1, so the standard topology which is considered usually is a topology generated by the supremum norm of a function. In this case, we have shown that this set and this mapping and this mapping in the standard topology, they are actually continuous. Now consider another topology on this set, namely this set. It is of course a subset of the space. So this is a Cartesian product of real lines, and we have so many real lines. This is the mapping of all functions defined on the segment from 0 to 1. Here we have already discussed there is this product topology, and hence it induces a topology on a subspace, on a subset of this set. So let us consider X, so this set, with the topology which is induced from the product topology from this set. Show that this mapping is not sequentially continuous, and hence it is not continuous at any point x in this space. And show that this mapping is sequentially continuous, but discontinuous at any point x in x. So this is a home task. If you have questions, next week we may speak a little bit about this. But I expect that you are able, if you try to do it, you are able to solve this exercise. Okay, so I'm finished for today. But if you have questions, you are welcome to ask, and we will discuss them.
Actually, could you please draw once again the picture that how the random process I mean how the random process looks like with the time.
So now we just we don't speak about random processes. We just say that these are the mappings. So where it was, I guess it was here, but probably also here. Yes. So what we have here, we have. So is this clear that the t power of some set is just the set of all mappings from T to X. Is this statement clear?
Yes, I think it's clear.
Yes. So we have just all functions from T to X. So now if we have we are a random process. Actually, at the moment, nowhere. But if we take a random process like X, it is a family of random variables. Sorry that I use always X. Probably let me use it some other Xi. So let me use Xi. Xi is a stochastic process, which is a family of random variables, let's say. So we can consider it as a mapping from omega to the space. Yeah, so wait a minute. So first of all, what are these random variables? So if each random variable is a mapping from omega to, let's say, R, yeah, then the whole process can be considered as a mapping from omega to R to the power from 0 to infinity. So this is the product space of this type. So my T is now this interval, my X is this stuff. Okay, so since I have no assumptions on how good the paths of a process are, so I consider all possible paths. So this is the space of this type, depending on which time we consider. Yeah, and so if we consider stochastic processes in continuous time, so not in discrete time, but in continuous time, that is, we have a product space which is an uncountable product. And there are many interesting effects in particular, but it is a kind of next step when one considers measurability, yeah, because stochastic process is a family of random variables, but random variables are not just a mapping from omega to R, but it's actually a measurable mapping. So it's a mapping from omega with some sigma algebra into R with a Borel sigma algebra. So measurable with respect to this couple of sigma algebras. So when you consider it as a single random variable, then there should be also some measurability. And so one needs some sigma algebra here, yeah, such that this guy would be measurable as a mapping like this. And the sigma algebra is actually discussed in the theory of measure theory, which is this sigma algebra is just a product of sigma algebras, Borel sigma algebras. But we need, okay, so many copies of this sigma algebra. And this is nothing else but a product sigma algebra or cylindrical sigma algebra. So this is the smallest. So let me write it down in the proper way. The smallest sigma algebra or sigma field, if saying properly in English, such that all canonical projections are measurable. That is sigma of pt over ot in T. So the stochastic process, the random, as a whole, as a unique random variable from omega to this space, is a mapping which is measurable with respect to, so here we have this sigma algebra F, and here we have this sigma algebra which I have written here. This one. Okay, but this is a kind of next step when you consider sigma algebras. And since we have started to discuss stochastic processes, suddenly one more thing which should be said in this setting is that, okay, we have this product space. It's a topological space. We have a topology, product topology, and hence we can consider Borel sigma algebra on X. Yeah, so the smallest topology, the smallest sigma algebra, which contains all open sets. And now the next question is how this Borel sigma algebra, how this sigma algebra is related to this sigma algebra. So in the nice countable set, it is the same. That is, for example, Borel sigma algebra of Rn, natural numbers, is the same as this product of Borel sigma algebras, one-dimensional. But it is not always the case for this identity. So this is a bigger sigma algebra than this one. And this makes the life in the theory of stochastic processes much more interesting and complicated. But I guess this is not the topic for functional analysis, but rather stochastic processes. I'm not sure that if this was your question, but I think it's an important remark. Anyway.
Okay. Thank you. And I think my question is solved. Thank you.
Welcome. So further questions? Okay, seemingly this is not the case. Okay, so thank you for your participation in these lectures, because if there are no participants, I will not give a lecture. I just say it for so that you know this. I understand that when there is a possibility to watch the recording, it is this demotivates to visit the lectures. But once again, if nobody comes, I have no lecture. So, okay, see you next week. If you have some questions, suggestions, whatever, send me them by email. Also, I have added some extra guests to the mailing list. So all emails which I have received for adding to the mailing list, I have added. So welcome to the next lectures.